Okay, welcome back. I hope you had a nice break. The midterms will be handed out at the end of the class. Ashish has just gone to get them in my office with solutions. I hope you look at the solutions. There's more in the solutions than is strictly necessary. The midterm is partly intended as a learning exercise, and I hope you learn something from it. I didn't learn too much about it about the performance of the class because some of the questions were easy enough that practically everybody got them, and some of the questions were too hard for anybody to get. And so the distribution, what I would really like to get is a nice bell-shaped curve going from 0 to 100 with a median at 50 and the standard deviation about 25. And I got a much more compressed curve than that. So frankly, I didn't learn that much about relative performance. And I gather from Ashish that you've all been doing the homeworks and have been doing a fairly steady job on that. So, I think everybody is close to being in the same boat here. If anybody has concerns about their performance, of course, they're welcome to talk to me. Drop date is a little while off. If you're concerned about what your grade might be, I'll give you the best idea I can, but really it's going to come down to the final for most of you. So it's not too much to say here. I give the grade distribution in the midterm solutions, and from that you can figure out where you are relatively. And my grading philosophy is, at MIT in graduate classes, roughly they're half A's and half B's. I have that as a guideline in mind. I try to look for where the natural breaks are. I decorate the A's and B's with pluses and minuses, but I don't think anybody pays any attention to those. And in other words, I generally try to follow the MIT grading philosophy, so as I understand it. So are there any questions about the midterm or anything about the class as we go into the second half? No, I see some people aren't back yet. It's a somewhat reduced group. Maybe a couple of people decided to drop on the basis of the midterm. That sometimes happens. I don't think it necessarily had to happen this year. Or maybe people are just having an extended break. Okay, we're now going into conceptually a break, the second half of the course. The first half of the course, we're talking about trying to get to capacity, specifically on the additive white Gaussian noise channel. So far, all the schemes that we've talked about have been block coding schemes, which their Euclidean images wind up to be constellations in a finite dimensional space. This is the kind of picture that Shannon had when he wrote his original paper on capacity and information that started off information theory. Basically, he proved that you could get to capacity on any channel with a randomly chosen code. In the setting where we are, that would be a randomly chosen binary code where you just pick all the bits of all the code words at random by flipping a coin. Okay? Just construct a code book at random. And as the code gets long enough, that's going to be good enough to get to capacity. This is a block code. 2 to the nr bits in length n code words where r is the rate of the code. That was a brilliant achievement to show that you could get to capacity by doing that. If you can do it by choosing codes at random, then there must be some particular codes that are good. Otherwise, the average over all codes wouldn't be good. So people started to go out to find good codes. And there was a fairly quick realization that Shannon hadn't addressed some key parts of the problem, particularly the complexity of encoding and decoding. The complexity of encoding was pretty quickly recognized to be not much of an issue because Peter Elias and others proved that, at least for the kinds of channels we're talking about, which are symmetric, linear codes are just as good. A random linear code will get to capacity. In other words, say a block code with a randomly chosen generator matrix. You pick k generators of length n, again by flipping a coin. That's good enough to get to capacity. All right? So, and we know we can encode linear codes with polynomial complexity. It's just a matrix multiplication to encode a linear block code. All right, so encoding isn't the problem, but decoding. What kind of decoding have we talked about so far? I guess, particularly with Reed-Solomon codes, we've talked about algebraic methods, but our generic method is to do maximum likelihood decoding, which basically involves computing a distance or a metric to each of the code words, exponential number of code words, 2 to the nr code words. So we have exponential complexity if we do maximum likelihood or minimum distance decoding. And that's, of course, was the motivation for doing some of these algebraic decoding methods, which were the primary focus of coding theory for several decades. A great deal of very good effort went into finding good classes of codes that were algebraically decodable, like Reed-Solomon codes. BCH codes, Reed-Muller codes, don't have such, well, they do, we now realize. But that was the focus. And with the algebraic decoding methods, there was polynomial complexity. But it began to be realized that these were never going to get you to capacity because of their difficulty in using reliability information, because most of them are bounded distance character. And in fact, that's still true. You can't get to capacity with algebraic decoding methods. So in parallel with this work on block codes, there was a smaller stream of work that has broadened, I would say, is the ancestor of the capacity approaching codes of today, on codes with other kinds of structure, and specifically dynamical structure, which is what we're going to talk about when we talk about convolutional codes. And this is broadened into the field of codes on graphs. And codes on graphs are nowadays the way we get to general capacity. All right, so that's really where we're going in the second half of the course. We're going to preserve the linear structure. Linear is always good for the symmetric channels we're talking about. But in addition, we're going to look for other kinds of structure, which are in particular suitable for lower complexity decoding methods, are suitable for maximum likelihood or quasi-maximum likelihood decoding methods. All right, so that's our motivation. Okay, convolutional codes. Convolutional codes were actually invented by Peter Elias in an effort to find, just as you can put a linear structure on codes without harming their performance, he was trying to find more and more structure that you could put on codes while still being able to achieve capacity with a random ensemble. And he invented something called sliding parity check codes, which, if you let the block length go to infinity, become convolutional codes. All right, and as I say, there was a trickle of effort, basically motivated by the fact that whenever people did a practical comparison of performance versus complexity, convolutional codes always beat block codes. And so, for instance, I was at a small company that was trying to apply coding theory. We quickly gravitated to convolutional codes because they always gave us a better performance complexity trade-off than block codes. And I'm going to try to indicate why that's so. All right, so I think the easiest way to understand convolutional codes is by example, by putting down an encoder. And the canonical example that everybody always uses is this one, so why should I be any different? You don't need that. Here is a rate 1/2 constraint length 2 convolutional encoder. And it has, it operates on a stream of bits coming in. So what we have here is a time index stream of bits, UK. All right? And you can think of this stream as being infinite in length. We'll talk about how to make it a little bit more, how to make this a little bit more precise as we go along. And we have a shift register structure here. The incoming bit UK is D, means a memory element or a delay element. It goes into a flip-flop. It's delayed for one time unit. There's some discrete time base going on here, which is indexed by K. So K is simply the set of all integers, comes the index set. Here's UK, here's UK minus 1, here's UK minus 2. All right, and constraint length 2 means that we have the present information bit. This is called the input or the information bit. And the 2 past information bits are saved. And from that, we generate 2 output bits. Y1 at time k is given by UK plus UK minus 2, where this is a mod 2 sum. Everything is in F2. Y2k is the sum of UK plus UK minus 1 plus UK minus 2. All right, so this is where we get the redundancy. What are we generally doing with coding? We're adding redundant bits in order to get more distance between the sequences that we might send, and thereby hopefully to get a coding gain on the additive white Gaussian noise channel. Here the redundancy comes from the fact that you get 2 bits out for every bit that you put in. All right, so there ought to be the possibility of getting some distance between possible code sequences. The code sequences here are infinite or semi-infinite. All right, but nonetheless, we can establish some minimum distance, or as it's called in this field, the free distance. Okay, there are 2 kinds of structure here. First of all, this is a linear time invariant system. It's if we were talking about the real or complex field, we might call this a filter. All right, or it's actually a single input, 2 output filter. So each of these, Y1k is a filtered version, the Y sequence is a filtered version of the U sequence, Y2 is a filtered version of the U sequence. All right, it's linear basically because it's made up of linear elements, delay elements, and mod 2 adders over the binary field, and it's time invariant because if I change the time index, it just doesn't really change the equation. It's very hand-waving rough here. But so it's a linear time invariant system, and we can analyze it the way we analyze a filter. It's redundant, so it has more outputs than inputs, as we want in a coding system. But other than that, we're going to find that the same kind of techniques that we use for analyzing discrete time linear filters can be used to analyze the system. It's just over a different field, F2, rather than R or C. All right, so that's one kind of structure. And secondly, it's a finite state system. Let's forget about all the algebra. There's a discrete time system which has 2 memory elements in it, each capable of storing 1 bit. So how many states are there in the system? 4. There are 4 possible states. that reflect everything that went on in the past. And that's all you need to know about the future, is what the state is at time k to see what's going to happen from time k onwards. All right, so this is a simple four-state system in this case. In general, if we build similar encoders out of shift registers, even if we put feedback in them, it's going to be a finite state system. All right, so we're going to restrict ourselves to finite state realizations, finite state encoders. All right, and that's going to ultimately be the basis for the decoding algorithm, which is going to be the Viterbi algorithm, which is a very efficient decoder for any finite state system observed in memoryless noise, which is what we have here. Hidden Markov model, sometimes called. All right, so we're going to interplay these two types of structure. All right, and I feel it's really the fact that that convolutional codes have these two kinds of structure that makes them better than block codes. They have just the amount of algebraic structure that we want, namely the linear structure. They don't have too much algebraic structure beyond that. We don't have elaborate roots of polynomials and so forth as we do with Reed-Solomon codes. We have a pretty modest algebraic structure here, and it's sort of different in character than the algebraic structure of Reed-Solomon codes. It seems to be the right kind, and it's married to this finite state dynamical structure, which is what allows us to have low complexity decoding. All right, so that's kind of the magic of convolutional codes. Not that they're very magic. All right, this is a convolutional encoder. What is a convolutional code? The convolutional code is roughly the set of all possible output sequences. And this is where we're going to measure the minimum distance of the code, minimum free distance. What's the minimum Hamming distance between any two possible output sequences? All right. And in the notes, I go into considerable detail to explain how we choose the particular definition of all. What do we mean? Do we mean the set of all possible output sequences if we put in a finite input sequence, an input sequence that starts at time 0 and is polynomial, let's say, it ends at some finite time? Or are we going to allow semi-infinite, bi-infinite input sequences? So you see there's some choices to be made here. And actually, it's of some importance that we make the right choice to get the proper insight into these codes.
Choose the initial state, right?
Excuse me?
We have to choose the initial state.
Yeah, okay. You know from linear systems that the output isn't even well defined unless you say what the initial state is. And in general, in linear systems, we say, well, we'll assume it starts out in the all zero state. Okay, and that's basically the choice I'm going to make, except I'm going to do it in a couple of steps. All right, but that's the right question. How do we initialize the system? That's a part of the specification of this encoder. And of course, we initialize it in the all zero state. But for that reason, in a general system, we can't allow bi-infinite inputs because if we don't know what the starting time is, we don't know how to define the starting state. Again, I'm speaking very roughly. So let me speak a little bit more precisely. We're going to define the set of all Laurent, which means semi-infinite sequences over the binary field. And this is called F2 of D. And this means a sequence, U say, which has only a finite number of non-zero terms before time 0. In other words, it can start at any negative time, but it has to have a definite starting time. I'm not talking about the set of all power series or set of all sequences that start at time 0 or later. The sequence can start at any time, but it does have to have a definite starting time, and before that, it has to be all 0. All right? So that, for instance, the sequence that I haven't introduced D transforms yet. Maybe I should do that immediately. But a sequence which at -5, -4, -3, -2, -1, 0, these are time indices, looks like 1, 0, 1, 0, 0, 1, 0, and goes on indefinitely into the future, but has all zeros back here. That is a legitimate Laurent sequence. Whereas a sequence that's ... 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so forth, all ones forever, is not, because it doesn't have a definite starting time. Okay. And I've sort of, all right, in this notation, I need to introduce D transforms. The D transform of a sequence U, which has components UK for K and Z, is simply the sum of UK D to the K. And we write that as U of D. Okay, for all K and Z. This is simply a generating function. It looks very much like the Z transform that you see in discrete time linear filter theory. We would write for something up here, so a sequence that is 1 at time 0, 0 at time 1, 1 at time 2, if U is equal to that, and 0 at all other times, we would just write U of D equals 1 plus D squared. So it's a generating function. It gives us a nice, the D just gives us a location of where the ones are. It's easier to write this than this, frankly. It's actually hard to write the sequence which is 1 at time K and 0 at all other times in this notation, but it's simply D to the K in this notation. All right. D here is algebraically simply an indeterminate or a placeholder. And this is the subtle difference from Z transforms. So Z transforms, we would write U of Z minus 1 equals 1 plus Z minus 2 for something like this. There's this Z to the minus 1 convention in Z transforms. That's not the important difference. We could clearly use D to the minus 1 rather than D. The important difference here is that Z is usually imagined to have values in the complex plane. All right, we look for poles and zeros in the complex plane and so forth. And so the Z transform really is a transform. It takes you into the frequency domain. If you make Z equals e to the j omega t or something, then you're in the frequency domain. Here, this is still a time domain expression, just as a convenient, compact generating function notation for a particular sequence. All right? So that's when I say the set of all semi-infinite sequences. Now I can write a Laurent sequence always looks like this. It starts off at some particular time. Let's say the first term is ud d to the d plus ud plus 1, d to the d plus 1, plus so forth. It always looks like that. So it has a definite starting time d, which is called the delay. The delay of u of d is equal to d in this case. And d can be any integer. It can start at a negative time or at a positive time. We don't require it to start at time 0 or later. But nonetheless, the sequence has to look like this. All right? And we indicate the set of all such sequences here. One of the immediate observations that you can make is that this is a time-invariant set, which the set of all sequences that start at 0 or later is not. If the set of all sequences that start at 0 or later has a definite time in it, and a set is time-invariant if d times the set is equal to the set. So what is d times f2 of d? I claim it's just f2 of d all over again. And in fact, d to the k for any k is equal to f2 of d. So the set of all Laurent sequences is time invariant, whereas the set of all power series in d, that's sequences that have delay 0 or greater, is not time invariant. It does not satisfy this. Okay? All right, chew on that. All right, an important consequence of this is that the set of all Laurent sequences forms a field. All right? Let's see what we need to prove for a field. Can we add Laurent sequences? Yes, we simply add them in the usual way, component-wise. Same way as you do in polynomial addition. You just gather together the components at time k. Can you multiply Laurent sequences? All right, you can certainly multiply polynomials. 1 plus d times 1 plus d is 1 plus d squared over f2. Can you multiply Laurent sequences? Well, yes, we can define multiplication by convolution as we do with polynomials. In other words, u of d times v of d is the sequence w of d, where wk is the sum over k prime in z of u k prime v k minus k prime. Now, what's the potential problem that can arise when you define multiplication by convolution? If any of these terms were infinite, we have no notion of convergence over f2. So we really have no way of defining an infinite sum. An infinite sum of elements in f2 is, in general, not well defined. But from the fact that each of these starts at one time, this is basically multiplying something by the time reversal. We only have a finite number of elements in any such sum. And so that's the real reason for using the set of all Laurent sequences. If we had set of all bi-infinite sequences, then multiplication would not be well defined. But by insisting that they have a starting time, we ensure that convolution is always well defined. Therefore, multiplication of Laurent sequences is well defined. Okay, so we have addition, we have multiplication. Maybe I'll go over here. What else do we need for a field? So far, we just have a ring. Inverses, yeah. Let's directly check inverses. So suppose I have some Laurent sequence, u of d equals ud d to the d plus so forth. Does that always have an inverse? In other words, we want to find something 1 over u of d equals what? Well, let's just divide u of d into 1 by long division, and we can get an inverse. Let me just give you an example. Suppose u of d is equal to 1 plus d. What's 1 over 1 plus d? We take 1 plus d, we divide it into 1, we get 1 plus d, d plus d, d plus d squared, so forth. So we get a semi-infinite sequence, not a polynomial, but nonetheless it's a legitimate Laurent sequence. It's actually a very simple periodic sequence with period 1. Are you with me on this? Could you find the inverse of any sequence that starts at time 0, let's say? If you can do that, you can certainly find the inverse of any sequence that starts at time d. You just multiply by d to the minus d. All right? So, every non-zero sequence, Laurent sequence, has an inverse 1 over u of d, let's say, which is also a Laurent sequence. Of course, as always, we can't divide by 0. But that, for the definition of a field, that doesn't matter. We have inverses. We check the associative, distributive, commutative laws. They all work. So this is actually a field. All right? Yes?
So polynomial multiplication would actually change convolution for the...
Yeah, if, the Laurent sequences certainly include polynomials. And this is the same as, this is consistent with polynomial multiplication. So it's just extending polynomial multiplication really as far as we can to these semi-infinite sequences that are semi-infinite in the future, but not in the past. They're infinite in the future, not in the past. Okay.
Actually, just an infinite sequence of linear equations that we get, right? First equation we get for the inverse. I mean, suppose we want to make
I
this,
missed the preamble. Could you start again?
I mean, to find the inverse, we just have to keep solving a set of linear equations, right? Where from the first equation we get the first term, from the second one by substitution we get the next one.
Yeah, it's long division, which is the same as the Euclidean division algorithm. We want to find a coefficient here that reduces the remainder to degree, to start at time 1 or later, to have delay 1. And we want to find the next coefficient to make the remainder have delay 2, and we can always continue this ad infinitum. All right.
It also applies to semi-infinite sequence. You have to do the same thing here.
These are semi-infinite sequences. Do you mean sequences that start at time 0 or later, which are called formal power series? Again, they're a sub...
What you meant was, suppose this UD is semi-infinite.
Yes, the UD is infinite.
Oh, sorry. Yes, of course, we need to check that. But you can see, it doesn't matter. We could divide by 1 plus d squared plus so forth, and the algorithm is the same. In that case, of course, if we did that, we get 1 plus d squared plus so forth, d plus d squared plus so forth. And what do you know? D times that is that, and we get 0, and it terminates after 1. All right, so yeah, thank you. Long division also works if we divide by any Laurent sequence. It's the same algorithm. Excellent. Okay, so every Laurent sequence has an inverse. In general, what do the inverses of polynomial sequences look like? Inverse of a polynomial sequence can anyone guess what its special property is? What is a polynomial sequence, first of all? I'm going to say a sequence is finite if it only has a finite number of non-zero terms. I'm going to say it's polynomial if it's finite and also causal. Causal means it starts at time 0 or later. Its delay is non-negative. All right, so that's the polynomials that we're already familiar with. What does the inverse of a polynomial sequence look like? What's this? It's always going to be infinite, right? Unless it's 1 or something. So unless it's an invertible unit in the polynomials, it's going to be an infinite sequence. But it's going to have a property. Nobody can guess what the property is going to be? I already mentioned it once. Periodic, right. And this is an if and only if statement. I guess I have to elaborate a little bit, but roughly that's correct. This is going to be one of your homework problems. Maybe I'm jumping ahead a little, but there are a couple of ways of seeing this. One is to use some of the algebra we did back in Chapter 7, but since we didn't really complete that, I won't do that. A second one is to see that in this long division operation, again, if I'm dividing by a polynomial, there's only a finite set of possible remainders that I can get up to shifts by multiples of d. So if I see the same remainder again, if I see 1 and then d squared, of course the series is going to have to continue in the same way. And since there are only a finite number of remainders, it's got to repeat at some point. Or a way that I can do it, which is more in the spirit of this, suppose I consider the impulse response of a system whose with feedback, which is set up so that the impulse response is equal to, in this case, say 1 over d plus d squared. You see that the impulse response of this is going to be 1 over 1 plus d squared. If I put in a 1 at time 1, then next time I'm going to get a 1 in here. I'm going to get a 1 feeding back there. Well, anyway, I believe that's right. This gives an impulse response of 1 over. If it doesn't, then readjust it so it does. Now, after time 0, the input is always 0, so I just have an autonomous system which is producing the terms at time 1 and later of 1 over 1 plus d squared. And again, it's a finite state system. All right, because we're over F2, there are only 4 states in this system. All right, so what can its state transition diagram possibly look like? First of all, the 0 state always goes around to the 0 state. So, the other states are interconnected in some way. And at best, they're always going to cycle. All right, so this is a quick proof that 1 over 1 plus d squared, in fact, any polynomial inverse is going to give you a periodic response. What I should really say is, let me define a rational Laurent sequence. I'll leave out the Laurent. A rational sequence is something of the form n of d over d of d, where these are both polynomial, or they're actually finite. Let's say they're both polynomial. You can reduce it to lowest terms if you like. Actually, I should make this finite up here so that it can have start at time before time 0. And I have to have d of d not equal to 0. And in fact, I generally require d naught, the first term down here, to be 1. So this is a polynomial with time 0 term equal to 1, like 1 plus d squared. So a rational sequence is one that looks like that. We can generate a rational sequence by feeding n of d into a sequence, into a system that has response 1 over d of d. And the output, I forget where you take the output off here, probably here. This will be n of d over d of d. Okay? There's a linear system, single input, single output. If it has impulse response 1 over d of d, then if I put in a sequence n of d, I'm going to get out n of d over d of d. And so by the same finite memory argument, n of d over d of d is going to be eventually periodic. So rational sequence, a sequence is rational if and only if it's eventually periodic. And again, on the homework, I'm going to ask you to prove this more carefully. You can use this finite memory argument if you like. So this should remind you of something. This should remind you of real numbers, integers, ratios of integers, which are rational real numbers, all that sort of thing. What are the analogies here? In the real numbers, the set of, first of all, how big is it? How many real numbers are there? It's uncountably infinite, right? How many Laurent sequences are there? You can, I think, quickly convince yourself that it's uncountably infinite. All right. Now we have a special subset of the real numbers called the integers. Oh, let's think of this as a decimal expansion, by the way. So we have a d minus 1, so forth, down to a naught, decimal point, a minus 1. These are the coefficients of a decimal expansion. There's something interesting here. Implicitly, we always assume that there are only a finite number of coefficients in the decimal expansion above the decimal point, right? There can be an infinite number going this way. So that's completely analogous to what we have here. All right. What are the integers? The integers are the ones that stop at a0, all right? That are all 0 to the right side of the decimal point. Over here, we have something that looks like ud d to the d plus ud plus 1, d to the d plus 1, and so forth. And in here we have a special subclass called the polynomials in D. And what are these? It's not precisely analogous because I should really do it with z minus 1 to make it analogous and expand it in the other direction. But these are the ones that have only a finite number of coefficients to the right of the time 0 point again. This is, we noticed before that there's a very close relationship between the factorization properties of Z and the factorization properties of the polynomials. They're both principal ideal domains. They're both unique factorization domains. They're both rings of the very nicest type. Okay, then we have in here the rational numbers. That's certainly an important subset of the reals. How many rationals are there? A rationals, this is basically a ratio of integers. And there's only a countably infinite number of rationals, right? And what's the distinguishing characteristic of the rationals in terms of their decimal expansion? It's eventually periodic, right? All right, so these correspond to the rational functions, which are denoted by this, the regular parentheses bracket. So this is the polynomials. This is the rational functions. And because these are eventually periodic, or because all of these can be written as n of d over d of d, and both of these are polynomials, or these are clearly countably infinite sets, this is a countably infinite set of all rational Laurent polynomials. So again, this is just mnemonics. I haven't proved anything, but the behavior of these things very closely reminds you of the behavior of these things over here. It's good to keep this in mind. One other point, suppose I'd allow by infinite sequences, then 1 over 1 plus d doesn't have a definite expansion. All right, it has two expansions. 1 over 1 plus d, if we require that the expansion be Laurent, then we only have this possibility. But if it could be by infinite in the other direction, then you can see that this is also equal to d minus 1 plus d minus 2 plus d minus 3 plus so forth, semi-infinitely. So another reason we want to rule out non-Laurent sequences is to have a unique inverse. This is just another way of saying that the Laurent sequences form a field, but the by infinite sequences don't have the multiplicative property. They're simply a group. Again, this is all written up in the notes. All right, so where I want to get to eventually here, come back over here. Let's now analyze this convolutional encoder. It's a linear time invariant circuit. That means it's characterized by its impulse response. Or responses, if you like, because it has two outputs. What does y1 of d, if I write the d transform of y1, what is that going to equal to? If I just put in a single impulse, single 1 at time 0 for uk, what am I going to get out of up there? I'm going to get out 1, 0, 1, and then all zeros. All right? So y1 of d, the impulse response, two steps, g1 of d equals 1 plus d squared. All right? That's the impulse response of the first output. And y1 of d is simply u of d times 1 plus d squared by linearity and time invariance. All right? So So if I put in 1 plus d squared, I'll get out 1 plus d fourth. Okay? Is this too quick? This is just linear system theory. You've all seen this in digital signal processing or something. Right? This is undergraduate stuff, except we're over F2. Okay? You just got to check that it's linear, it's time invariant, therefore it's characterized by its impulse response. And so once you know the impulse response, you want to know the response to any sequence. You convolve that sequence with the impulse response. This is that statement in D-transform notation. Okay? People happy with that? I don't want to... I will spend time on it if it's mysterious, but I don't think it should be mysterious. All right, and let's complete the picture. What's the impulse response for the second output in that picture? 1 plus d squared. Thank you. So we have y2 of d is equal to u of d times 1 plus d squared. And, or we can aggregate this by simply saying that a little 2 vector y of d is equal to a 1 vector u of d times a little 2 vector g of d, where this means y1 of d, y2 of d, and this means g1 of d, g2 of d. Okay, so this is a very simple little matrix equation. And now the convolutional code, this is the output sequence in response to a particular input sequence u of d. So we're going to define the code as the set, as I said, the set of all possible output sequences when the input sequences run through what? And we're going to let the input sequences, now with all this elaborate setup, so it's the set of all output sequences, y of d equals u of d, g of d, as u of d runs through the set of all Laurent sequences. It's sequences that start at some definite time. And now I've said much more precisely what I said back at the beginning. Because all sequences have a definite starting time, we know what the starting state is for any of these sequences. Always when the sequence starts at time d, the system is quiet. It's in the all zero state, and it's driven from time d onwards. So this convolution is well defined. If we had an undefined starting state, then this would not be well defined. Okay, so a longer than I intended lecture on Laurent sequences, but it's turned out in the theory of convolutional codes, it's very important to get this right. People have used various definitions. They've let this run through finite sequences, polynomial sequences, formal power series, and trust me, this is the right way to do it. All right? And I don't think anyone is better qualified to make that statement. So that is the way we define a convolutional code. Now, which direction shall I go from here? I guess I ought to ask, what are we going to allow g of d to be? In the picture up there, we have g1 of d and g2 of d polynomial, which means both causal and finite. Causal means it starts at time 0 or later. Finite means that it has only a finite number of non-zero terms. Okay, I want to allow perhaps more general types of encoders. I do want the encoder to be finite state. So let me impose that I want the encoder to be finite state. But I'm going to allow feedback. Which I don't have there. If I allow feedback, then I can get infinite responses, infinite impulse responses. But by the same argument that I've already made, they're going to have to eventually be periodic, right? If the encoder has finite state. So we have to have G1 of D and G2 of D, or in general, we're going to allow up to n of these for rate 1 over n encoders. If we want this to be the impulse response of a finite state encoder, well, they also have to be causal, don't they? In order to be realizable, it has to start at time 0 or later, the impulse response. Then I'm going to have to require that these all be rational and causal. All right? And that's the only limitation that I'm going to put on the G of D. All right? So in order to get a finite state system, I need to have rational impulse responses. In order to have a realizable system, I need causal responses. Okay? So these are the requirements on the impulse responses. Otherwise, I'm not going to force them to be anything in particular. Now, let's see. I go into realization theory a little bit in the notes. Since I've spent so much time on Laurent sequences, I don't think I'm going to do that here. Yeah?
Does it just mean that the denominator is also polynomial, right?
Correct. Right. So, in fact, let me always write these. Let me take the least common multiple of all the denominators. I'm going to write these then. G of D is going to be some vector of polynomials up here. I can always write the least common multiple of all the denominators down here and have a single denominator. Okay? So this is going to be my general form for a causal, rational, single input and output impulse response. It's going to consist of something like this, where these are all polynomial. This is a single polynomial with d naught equals 1. Turns out that's necessary for realizability. And I'll just tell you the fact, which you can read about in the notes. And in fact, I leave this mostly as an exercise for the student anyway. Realizable with nu equals max of the degree of the ni of d, or the degree of the denominator. In other words, I take all these polynomials, the maximum degree of any of them, let me call that nu, and I claim there's a realization with nu memory elements. And of course, I'm going to assume here that I've reduced this to lowest terms in order to keep that down. Now, if I didn't have the denominator term, this would be clear. If I just had g of d equal to a set of a vector of n polynomials of maximum degree nu, then it's clear that just by this kind of a shift register realization of, here we call the constraint length equal to the number of memory elements, I can realize any n impulse responses which all have degree nu or less, right? So the only trick is showing how to put in a feedback loop which basically implements this denominator polynomial d of d. If I start off by realizing 1 over d of d, then I can basically just realize this in the same way. All right? And nu is called the constraint length. And I have 2 to the nu states. Okay, so by constraining this to be of this form, I forced myself to have I've now gone full circle. The number of states is in fact 2 to the nu, and in particular it's finite. Okay, so I have when I constrain the impulse responses to be like that, then I guarantee that I'm going to have a finite state realization. All right? So from now on, that's what my impulse responses are going to look like. All right, now let's talk about code equivalence or encoder equivalence. I've defined the code generated. Now I'm going to characterize an encoder by its impulse responses, G of D. The code generated by G of D is U of D, G of D, as U of D goes through a set of all Laurent sequences. 2 encoders are equivalent if they generate the same code. Seems reasonable. What we're really ultimately interested in communications is the behavior of the code, in particular the minimum distance of the code. How far are the sequences separated? We're not particularly interested in the encoder. At the decoder, we're just simply going to try to tell which code sequence was sent. So for most purposes, probability of decoding error, performance of the decoder, and so forth, we're only interested in the code itself. We're not interested in this little one-to-one map between information bits and the code sequences. So this is a reasonable definition of encoder equivalence. Now, for the case of rate 1 over n codes, which is all I'm talking about here, 1 input, n output, so that the code generator looks like this. It's very simple. G of D and G prime of D are equivalent if and only if G of D and G prime of D differ by some multiple A of D, where I could let A of D be any Laurent sequence, but then to keep everything in the same ballpark, I think I have to keep A of D rational and causal. But even forgetting this, in other words, if one is a multiple of the other, then the 2 codes are equivalent. That's clear because I can invert A of D. So this is just a single Laurent sequence, has an inverse. This is the same thing as saying G of D times 1 over A of D, which is another rational causal sequence, is G prime of D. If this is true, then the sequence generated by U of D when the encoder is G of D is the same as the sequence generated by U of D, A of D, when the encoder is G prime of D. And this is another rational sequence. And vice versa, the code sequence generated by U of D if the encoder is G prime of D is the sequence generated by U of D over A of D if the encoder is G of D. Okay, so that's really the proof. So this is a very, very simple theorem. In other words, I can multiply any encoder n-tuple, g of d, by any rational causal sequence out front, in particular by a polynomial or 1 over a polynomial or something, and I'm going to generate the same code. This is not going to matter. Now, to see why we might want to make use of this, let's see. Well, given this, we might want to pick some particularly nice encoder, all right, from this equivalence class of encoders, all of which generate the same code. And basically, I'm going to suggest that the nicest encoder is the one we get if we multiply by d of d, and if there's any common factor of these n of d's, we divide it out. All right, that'll give us the least degree polynomial encoder, which is equivalent to the given encoder. If I start off with one like this, and I want to multiply through by the denominator to make it polynomial, and if there's any common factor to the numerator, I want to divide it out. And that's what I'm going to take as my canonical encoder. Now let me give you a little motivation for that. That's one motivation. It'll have the simplest realization. It'll have a feedback-free realization by getting rid of the denominator term. And it'll have the least constraint length of all equivalent encoders, and that's a theorem too. But that's not the primary motivation. Let me talk a little bit about distance at this point. Let me take my example encoder again, and let me ask what's the minimum distance between code sequences. This is clearly going to be an important performance metric of this code, right? How would you go about answering that question? There are at least two reasonable ways to go. Do you think the minimum distance is greater than 1?
No.
You think it's 1? Okay. So how would you get two sequences that differ in only one place?
I mean, if you take the impulse response, or if you take the...
Well, the impulse response, if I put in 1, u of d equal 1, then I get out g of d, which in this case is 1 plus d squared, 1 plus d squared. I actually get a weight 5 sequence out. You see that?
You get 1, 0, 1.
Yeah. So I get this out in D transform notation, or I get 1, 0, 1, 1, 1, 1 in terms of that times 0, 1, 2, so forth. y1 equals this, y2 equals that, right? Okay, so that's a weight 5 sequence. Certainly, if I put in the all 0 sequence, I get out the all 0 sequence. So, as always, the all 0 sequence is an element of the code. This differs from the all 0 sequence in 5 places. So, all you've shown me so far is the minimum distance is not greater than 5. I found 2 sequences that differ in 5 places. Are there any that differ in fewer places than that? The answer is no. So, in fact, this is called the free distance. For this code, the so-called free distance is 5. Let's think of the 2 different kinds of structure for this code, and they lead to different but complementary arguments that both get us to this conclusion. First of all, the code is linear, right? So C is linear. Is it not? If I have y of d equals u of d, g of d, and y prime of d equal to, say, some other sequence, u prime of d times g of d, then let me check the group property, which is all I have to check for a binary code. And I find that y of d is the sequence, the sum of these two sequences is the sequence that's generated by the sum of the two input sequences that led to these two sequences. So the binary sum of any two sequences is another code word. All right, ergo it has the group property. Ergo C is a group, and that's all we need to check. It's actually linear over F2 as a vector space over F2. Because 0 is in the sequence, and 1 times this, 1 times any code word is in the code, excuse me. 0 is in the code, and 1 times any code word is in the code. So we've checked closure under vector addition and scalar multiplication. All right, so it's linear. What is the main conclusion we get from this? Therefore, the minimum distance between code sequences is equal to, anybody? The minimum non-zero weight of any y of d in the code. Okay? It's exactly the same argument. We're talking infinite sequences here, but there's nothing that changes in the argument. And so that really simplifies things. We simply have to ask, here's a non-zero sequence of Hamming weight 5. You can add this to any code sequence and get another legitimate code sequence. This is a code sequence, add it to any other, and you get a legitimate code sequence. So from any other code sequence, there's going to be one of distance 5. Are there any lower weight sequences in this code? Well, what would you...
The first place will have at least 2.
Good. So here's where we need to get into much more concrete arguments. You can see that, first of all, we're only interested in looking at finite sequences in the code. And we may as well have them start at time 0, because if they start later, we could just shift them over by time invariance. So we're only interested in finite polynomial sequences that start at time 0. Okay? So just as you said, in the first place, they're always going to have bing, bing, 2 1s. When the first 1 comes in, we're going to get 2 1s out, for sure. Time 2. This is what we get out if the second bit in the input sequence is a 0. What happens if the second bit in is a 1? Then we add this to this, shifted over 1. We add 1, 1 in particular at this place. We get a 1, 0 out. Okay? So we conclude at the second time, we're always going to get at least another unit of distance. Now jump ahead. However long this is, it's going to have to end at some time. All right? At the time when the last bit, the last non-zero bit is shifting out of the shift register, we're also going to get 1, 1 out. Okay? So any finite code word has to end with a 1, 1 at the last time out. People don't seem to be totally comfortable with this, so I'll do it in a more elaborate way in just a second. But this is the basis of the argument.
Why should they have the 1, 1 at the same place?
At the end?
No, I mean, why should they have 1, 1 at the same time?
At the end of a finite code word. All right, what does a finite code word consist of? I'm going to claim that we only get a finite code word out when we put a finite input sequence in. Okay? We have no feedback here. So there's going to be some last one in the input sequence. As that shifts through here, at the very last time, the last state is going to be 0, 1. All right, just before that comes out, there's a 0 coming in forever after. So at the last time, we get a 1 at UK minus 2, and that forces these two bits out to be 1. Or you can do it by polynomials. You can always show that if you multiply this by any finite polynomial, you're going to get highest degree terms both equal to 1. Okay, I'll do this by explicitly drawing out the state diagram. So we can conclude here that we always have 2 here, 1 here, dot, 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 and finally at the end we have to have at least 2. Therefore, every non-zero finite sequence has to have weight at least 5. Since we've seen one that has weight 5, that is the minimum distance. Okay? Now let's do this by drawing the state diagram, which is where we're going.
The last one we know right away the minimum distance for the goal.
No, we had to construct a little argument here and, in effect, make a little search. And this simple argument wouldn't work for more complicated cases. So let me show you how to attack more complicated cases. We want to draw it's a finite state machine. How do you analyze finite state machines? Well, a good way to start is to draw the state transition diagram. And I don't know what the curriculum consists of nowadays, but I assume you've all done this. We draw the 4 possible states, 0, 0, 1, 0, we can get 2 from 0, 0. 0, 0, if I get an input of 0, then I'm going to put out 0, 0, and I'm going to stay in the 0 state, all right? Because this is linear. If a 0 comes in, put out 0, 0, stay in the 0 state. Or a 1 could come in. And in that case, as we've noted, we'll put out 2 1s as our output, and we'll transition to the state 1, 0. Okay? Now from 1, 0, where can we go? From 1, 0, if a 0 comes in, then we'll put out 0, 1, and we'll transition to 0, 1. Or, to get another 1 in, we would put out the complement of that, 1, 0, because we get another 1, 1 in this linear thing. Work it out. I'll just assert that. And we go to state 1, 1. From 0, 1, if we get a 0 in, we return to the 0, 0 state. And we put out 1, 1. So here's our basic impulse response right down here. All right, we put in a 1, we go through this little cycle, we come back to 0, 0. Or if we get a 1 in, we go back up here, and at that point we put out two zeros. Is that right? Yeah, because it has to be the complement of this. All right, and if we're in the 1, 1 state and another 1 comes in, we stay in the 1, 1 state. And we put out what? Let me do the 0, 1 first. If we go 0 and we're in 1, 1 state, then when we get out a 0 down here, and we get out a 1 up there. We get out 1, 0. Or if we get in a 1, we put out 0, 1. All right, so that's the state transition diagram. Now, all right, again, let me make the argument that I made before, now a little bit more concisely. I guess we're going to have to stop. All right, so every path through this state transition diagram corresponds to a code sequence, right? Every finite or semi-infinite path. I always start in the 0 state. For a finite code word, I have to come back to the 0 state. Correct? So I'm always going to get 2 1s when I start out. Then the next time I'm either going to go on this transition or this transition, but either way I'm going to get at least another unit of weight. And then I can do whatever I want through here for a while, but eventually I'm going to have to come back out here. All right? And when I get back to the 0 state, I'm going to get 2 more 1s. All right? So that's maybe a lot easier way to see the minimum weight has to be 5. Okay, again, if it were more complicated, I'd have to make more of an argument. All right, next time when we come back, we'll talk about turning this into a trellis diagram. We'll talk about catastrophicity, which is where I was going with this canonical generator. It's just a minor algebraic point, but one you need to know about. We'll talk about the Viterbi algorithm. I think we can probably get through this chapter on Wednesday. Okay. Ashish has your midterms and the midterm solutions.